Hello, welcome to this lesson. We'll be talking about pressure in fluids. This is Science Tips, and you can follow us on YouTube at Science Tips 001. If you have not subscribed, please give us a subscription. You can also like and share this video for more videos. You can also visit our site or our YouTube channel, yeah, so that you get more science tips. You can also email us with questions or suggestions or comments. They are well invited. Look at kagianjdongo@gmail.com, and we'll appreciate very much. I hope you will enjoy this video and you'll learn something from it. Let us do a small recap of lesson 1. We had learned about pressure in solids, and we said that pressure is dependent on the force and surface area of a solid. It depends on how a body is lying or standing, and the extent to which it exerts pressure depends on the surface area. So we came up with this definition, or this equation, that pressure equals to force divided by area, or definition that pressure equals to the the total force acting perpendicularly per unit area. So in this lesson we'll be able to learn about pressure in liquids, and we'll be essentially looking at the effect of height of liquid column and density on pressure. And lastly but not least, we'll be looking at transmission of pressure in liquids, in what essentially we'll be talking about Pascal's principle. So welcome, continue watching and enjoy this video. To introduce on pressure in liquids, previously we had looked at pressure in solids, but remember that there's a difference between solids and liquids. Solids have definite volume, mass, and shape, but liquids have only definite mass and volume but have indefinite shape. Therefore, they take the shape of the container. So we can essentially calculate the pressure at the bottom part of a liquid, which will be acting as our cross-sectional area, by calculating the weight of the liquid depending on the volume, and if we have the density, we can be able to get the force or the weight. Yeah. So the pressure varies with height of the container. So height is a very important parameter in calculating the pressure in liquids. As we can see in this diagram on the right, the height of the two liquids is the same, and therefore we expect that pressure at the bottom of the two to be the same if area does not affect the cross-section area does not affect the pressure in liquids. So to that point, I think I have already started explaining it. Pressure exerted by the weight of water in a certain height may be calculated by the weight of liquid above that level and the surface area of a container. So if we expect the pressure in this container at a H to be a certain amount, then we expect even for the larger beaker, or the beaker with a larger surface area, to have the same pressure, because we are saying essentially in the fourth point that the pressure acting on the bottom level of the liquid does not depend on the surface area. And the reason is very simple, that liquids do not have a resultant force representing all the forces exerted by the individual molecules or particles of the liquid. Remember that each particle in liquids is more free, or it's not rigidly positioned at a certain point. It is free to move about, and that is why liquids flow and this makes the force exerted by different molecules not to be able to be added up to make the resultant force acting on the liquid. But now, essentially, when the water is put in a container, more or less, we can say that the force, the resultant force, is a representation of all the weights of the individual molecules, because the molecules are still, the molecules are not flowing about. We will see more as we continue with the lesson. We'll be able to look at why area or surface area is not a very important parameter in calculating pressure in liquids. But essentially, what we are talking about, the surface area or the cross-sectional area, uh, in this container, it's the same container, but it has been tilted a bit to look at the cross-section area. Uh, so we can essentially calculate or derive the formula for calculating pressure in liquids, and to be able to do that, we'll be able to look, we'll first look at a container containing a liquid to a certain height h, and the container, we are giving it the dimensions of a cuboid or a rectangular based prism. So for simplicity purposes, we'll be able to see that as we progress with the derivation. But we start by saying that as we had looked at in the previous video, pressure equals to force over area, or divided by area. That's what we had looked at in the other video, and we'll be using this. To derive another formula, you use what you have or what you know already, so to be able to get to what is an unknown. Uh, so we are saying that if the force applied is taken to be the resultant weight, because now this container is at a still position, we expect that the resultant weight of the individual molecules to be taken as the weight of the this liquid. That is, we are ignoring the weight of the container. Then pressure may be calculated as a pressure as liquid weight divided by area, where now the liquid weight will be equal to the force exerted by the liquid. We're also saying that but the weight of the liquid is equal to the product of mass and acceleration due to gravity. This is as provided by, we know that force is equals to mass times acceleration due to gravity, or acceleration, as provided by the second Newton's law of motion. Do not worry if you've not looked at it. Check out for a video on that and you'll be able to get it correctly. So we can essentially substitute the weight by mass times acceleration due to gravity, and this will give us the force acting on the area. Then we are saying that we can also use the density and volume instead of the mass as in the equation. So instead of using the mass, we essentially substitute mass with the density and volume. And the reason is very simple, because we do not want to be measuring the mass of the liquid at any instant. We want to determine the pressure. If we have a little amount of the liquid or more, we'll be able to get the pressure at a certain height, because the density is the same, does not change. And then we'll see how volume will be substituted later on as we derive this equation. We're also saying that substituting the expression for mass in equation 2, as we have done previously in the previous slide, the weight will now be equal to the density. Density is represented by this sign, which is in Greek known as rho. I, I expect that you are already familiar with this. And then the volume V, and then acceleration due to gravity G. So with our weight, we have the weight, and which is the same as the force. Now in the next step is to calculate the volume of the liquid in this container, in this case given by the dimensions, just a simple multiplication of the dimensions, the length times width times height. Remember, length times width gives us the cross-section area, and then multiplying it by the height gives us the volume. So if we replace it, we replace length times width times height in the equation 3. So we'll be able to replace volume with those dimensions, and then we'll be close to getting our new formula. So the area of the bottom is also given as area A equals to length multiplied by width. And now we can now substitute the volume and the area in the first equation, which we said equals to pressure equals to liquid weight divided by area. So essentially this is what we get: rho multiplied by g, then multiplied by the expression for volume, then we divide that by the expression for the area. So you can see that in this case we have length and width on both the numerator and the denominator side. Therefore, if they cancel each other pretty nicely, we'll be able to get that pressure equals to rho gh, or what we call the density multiplied by acceleration due to gravity multiplied by the height. Now you can start seeing why we are saying that height is a very important parameter in calculating the pressure in liquids. So, and the derivation, I hope, has been very simple and direct, and you've been able to follow through nicely. Now let us look at some few other things as pertaining the effect of height on the pressure and also the density. So to analyze the pressure in liquids, basically we start by saying that from the formula which we have derived up there in the other slide, pressure in liquids depends on three important parameters. That is the first one. If we can refer to the equation that pressure equals to rho gh, then pressure equals to those parameters will be density, height, and acceleration due to gravity pretty nicely. So we can say in liquids, pressure depends on height, depends on the density, and also depends on the acceleration. That validates the next activity as to why we are now analyzing how density or height affects pressure in liquids, or even the acceleration due to gravity. But remember, acceleration due to gravity on Earth is almost constant because it is on an averagely about 10 newtons per kilogram, but the height column, it varies depending on the amount of liquid, and also the density of the liquid changes depending on the type of liquid. So we can design a simple illustration or a simple demonstration to illustrate how liquid pressure depends on height and also on the density. So we essentially saying that you look for a plastic container, you make three vertical holes, or three holes vertically on a straight line, possibly if possible. That is to ensure that you have three jets that will be thrusting or throwing water out at different heights of the water column. So we'll be able to gauge the amount of pressure by the distance to which the water jets will be drawn. So we fill the container with water and make the observation. If you make such a design or a demonstration, this is what you expect to see, that you have the three holes made vertically in this container. Then make sure that you allow water to flow throughout so that all the columns will be throwing water out. So you can see the hole which is close to the bottom, near the bottom, will be drawing water at a higher pressure because the jet essentially will be drawing water to a further distance than B and C. And therefore we can say that pressure is higher at point A than point B, which is again higher than pressure at point C. So this is the conclusion that the hole near the bottom of the container draws water farthest, and we can be able to conclude that essentially at point A, that's where we say the pressure is highest. Not it's highest compared to B and C, but even below A, the pressure is even higher. Again, if we use a denser liquid than water, such as paraffin, we expect to have different results, but looking almost similar to this one. But if you look keenly, we expect that we have some difference in the distance to which the holes withdraw water out. Essentially, this is what we expect, that the denser the liquid, the further the jets will be thrown, or the liquid will draw water further than a lighter liquid. So essentially that is what we expect, such that if you compare the orange, or is it orange or red, the orange jet at point C is drawing water further than the black jet, which represents water essentially. The first one, or maybe the red one, will be the one representing paraffin. So this has been adapted from KLB, Secondary Physics. You can look at it in book 1, on page 1 or 2. You can be able to view this diagram better. So what we've learned is that the pressure increases with the depth, because at point A, which was at lower height, or was close to the bottom, it had greater pressure than the point B and C. So still having the same diagram, we'll be able to look at the pressures at different heights of the liquid in a container, and now we harmonize that with the equation that we've derived to see how pressure varies with depth. So this is the same diagram, and we are saying that pressures at point A, B, and C are different because the heights are different. Simply, the height makes the difference because density is the same and acceleration due to gravity is the same if the liquid used is the same. So if you can have these heights, the heights we are talking about is from the water top surface to the individual holes. So we have H1, H2, and H3 as the heights for C, B, and A respectively. So we are saying that to calculate pressure at point A, at hole A, we expect to use density times gravity, acceleration due to gravity, multiplied by height H3, which essentially will have a value, a definite value. If you do a demonstration, you'll be able to measure the distance so that you can calculate. Now at point B, again we expect that pressure will be equal to rho g H2, that is height will be substituted by H2, and we expect, because H3 is greater than H2, then automatically pressure PA, or pressure at point A, will be greater than pressure at point B, and also which will be greater than pressure at point C respectively. So you can say that PC also is equal to rho g H1. Yeah, so this illustrates why now we can say that pressure increases with depth. And we can make a very beautiful observation by taking the ratio of pressure at hole A and to that of hole B, we essentially will be coming to a conclusion that pressure at point A divided by pressure at point B equals to height from the surface to point A, which is H3, divided by height from the surface to point B, which is essentially H2. So we can conclude that the ratio of PA to PB equals to H3 to H2. So that's a very important observation. You can just keep it in mind so that you better understand this. So finally, we'll be looking at transmission of pressure in liquids, which is essentially the Pascal's principle. And to illustrate how pressure is transmitted in liquids, I like best using this illustration. If it was possible to make it a demonstration, it would serve better. So if we connect or we set up our apparatus like this, and we assume that we are using two syringes, P and Q, and two masses, so that they provide different amounts of force, we expect that if we place the first mass on syringe P, then we expect that the liquid in syringe P will go down to by a certain height, and the same amount of liquid which goes down into the rubber tube is again transmitted up into syringe Q. So when a force is applied to a piston, then we say that the liquid is pushed down syringe P. So we are talking about the piston on syringe P, and we're saying that what we should expect if the syringes are measuring the amounts or the volume of liquids which is transferred, then the same amount of liquid should be transferred to syringe Q. That is very pretty, and that can only work if we are saying that the liquid used cannot be compressed or is incompressible. So basically, we know to get to such an ideal state is not very much accurately possible, and are we are acknowledging that the liquid may be compressible, but to a certain we say to a very minimal value, which is which may not be considered, or it may be ignored. So it's a submission that the liquid may be compressible, but we are expecting in an ideal state the same amount of liquid should be transferred to syringe Q. Then, so therefore, we can say that the pressure applied at the piston in syringe P, we expect it to be transmitted to syringe Q, the same amount of pressure. So it's the same because the same amount of liquid is being transported. Then remember, pressure is equals to force divided by area, and in our derivation we were coming close to something like volume and area again, which will will make sure that the pressure that is applied on one point will be transmitted to the other side, because the same volume or amount of liquid is transferred. So what we are saying basically is that if the pressure applied on syringe or syringe P, or we call it pressure P, I don't know how we will be able to see that, or you'll be mixed up, is given by force over area, so it will be Fp over AP, and we are expecting that the same pressure will be transmitted to syringe Q. So the same pressure will be submitted, so that we have Fq over AQ to be equal to FP over AP. So if you are wondering where FP, AP, FQ and AQ are, you can look at that is where FP is. It's produced by the mass which is pressing down that piston on syringe P, and then the area P is the cross-section area of the piston which is pressing the liquid in syringe P. Yeah, there it is, that cross-section area, and then FQ again is there and AQ is there. So if you are saying that pressure is equals to force over area, so then FP over AP makes pressure on syringe P, which we can call PP. I don't know, PP, and then should be equal to force on Q over area of Q, which will be FQ over AQ, which will be equal to PQ. So essentially this is what we are talking about. Pressure on syringe P is equal or will be transmitted equally to pressure on syringe Q. So this demonstrates a principle governing the transmission of pressure in liquids, and it can be summarized as the Pascal's principle of, or what we call the principle of transmission of pressure in liquids. So it says that pressure applied at one point or one part of an enclosed liquid is transmitted equally to all other points or parts of the liquid, provided that the liquid is incompressible. So we are stressing again that the liquid should be treated as incompressible, even if we have some miniature compressibilities, or we have some small variations in volume. So that may be successfully ignored, or not ignored by, but what we say, we can assume. It's an assumption. Yeah, that's the correct word to use there. So Pascal's principle is also called the principle of transmission of pressure, and we are saying also that gases may also obey Pascal's principle if they could be incompressible, or their rate of compressing, or if we compress them, the volume does not change with a significant value, that is. So I hope uh, you've been able to get something from the video, and I am also saying thank you very much for watching us, and you can also subscribe, share, or like this video so that you get uh, more videos about pressure and pressure in liquids. So in the next video we'll be talking about pressure in gases, coming in a few moments. Thank you.